correspondence to study one particular case of this Bloch-Kato conjecture, which relates special error values to thermal groups. So fix imaginary quadratic field E and consider a pair of unitary groups, reductive dual pair, H and G. For H is sort of U3 and G is U22. Okay? So is a positive definite emission space, and the second is there is a fixed maximal isotropic decomposition. Okay, VT plus and VT minus. So the tensor product over E is emission space. I can also view it as a symplectic space over Q, and there is also a maximal isotropic subspace V plus and also V minus. So for Schwarz function phi, which is on the analytic point of this V plus, I can define theta theories. Just I take the wave representation and act on this one, but I sum over all the rational points. Okay, so this gives me this gives us automorphic form of this product group H and G. Okay. So now I want to do this theta lifting. So if I have an automorphic form F on this group H and also the theta theories from the previous slide, so I have this integral. I integrate F against this theta kernel on the group H. So this is the theta lifting of this automorphic form F by these theta theories. So one can show that this is in fact an automorphic form on the group G. So it is in particular invariant under the rational point of T. If I let F and this Schwarz function phi vary, then this will give the theta lifting of irreducible automorphic representations from this group G, from this group H to the group G. So I will write this as theta. This is a set of irreducible automorphic representations of H, similarly for G. And in fact, this works not just for the group in my case, H and G, but more generally, for example, for orthogonal, or this is a metaplectic cover of symplectic group. So it is two cover of the symplectic group, or similar, or in the other order, or for unitary groups UN, but with some signature are not precise here, or for the general linear groups. For example, the classical Schmarr correspondence, which takes half unitary weight, okay, of SR2 to even weight. This can be interpreted as a theta correspondence for this pair, for SR2 tilt to O3, yeah, but this in this case is O1. So this is the general framework for this theta correspondence. There is a very fundamental relation in this theta correspondence, which relates the Peterson products to the spatial error values. So in our case, there is this result of due to many people, Rodis, Kutala, Ganqiu, and Takeda, and Yamana, and many others, which says that if I take the Peterson product of this theta lifting, theta phi of F, and I divide it by the Peterson product of F, then this is the standard error value of this representation pi, evaluated at s equal to 1. Okay. Here I need to modify some error factors at a band primes, but here I do not precise here. So my remark is that this standard error function, this is a degree 6. If I write pi of E for the best change of the representation of automorphic representation pi from H to G03 then the Goldman-Jaget error function of pi of E of this best change is in fact equal to this standard error function. So for example, if this best change, this local component, if it is unramified principal series given by these three characters, then this is this local error factor is the product of these three derivative factors. Okay. So this is the automorphic side of the story. So the takeaway of this the result is that it relates the Peterson products, the recursion of two Peterson products to the special R values. But conjecturally, for example, here, this Peterson product is conjecturally is related to the adjoint R value of F, and this is related to the adjoint R value of this theta lifting. But this is only conjectural. We do not know any result in the literature not yet. But this Rayleigh's inner product can give the quotient of this one is an explicit R value. Okay. So for the Galois side, I fix a prime number, and under some technical conditions on the regularity of the weight of this automorphic representation pi on H, I can attach a Galois representation. So this is the work of Arthur and Mock. So of the Galois group of Q to the LQ group of H. So this I write it under G3. So this is semi-directed product of G3 with Z over 2. So there is some precise relations of this Galois representation, but I will not say anything more here. Similarly, for the theta lifting, I can also attach a Galois representation. So this is from the Galois group of Q to G4. Here, this group G3, I can embed it into GR6. So for for the group for this component, I can just embed it into the diagonal block diagonal group matrices G and G transpose inverse. But for the other component, just embed it as the anti-diagonal block matrix. So this will give us this standard R function, sorry, standard representation of this rho pi of this Galois representation. So this is just a composition of this rho pi with this embedding. Now there is the natural embedding of this G3 into G4. This will give rise to the decomposition of the two representation of this adjoint representation of this rho theta pi. So this adjoint representation of this rho theta pi is direct sum of these three representations. This one is adjoint representation of rho pi, direct sum with this standard representation of rho pi, and also this quadratic character. So if you count dimensions, this is dimension 16, this is dimension 9, and this is dimension 6. This is dimension 1. So finally, the main object of study is this standard Galois representation, this standard rho pi. So I can define for this Galois representation this thermal group. So it is the subgroup of this group cohomology with some local conditions for each prime. So for L given from P, this is unramified, but for the place of the P, it's more complicated. So I cannot give the details for the definition here. So this is the setup for the last side. So now I state the main result. So this is still work in progress. So I need to make some assumptions on this automorphic representation. So the first one is that I assume that the weight of the Archimedes component is positive, but it is smaller than P. Okay, it's smaller than P but positive. So I also assume that this quadratic character, normalized quadratic, directly R value of this character is a P unit. Second, I assume that this automorphic representation pi is everywhere unramified, and that this theta pi is a cuspital. In fact, this condition some other minor conditions will ensure that this is cuspital. Third, I assume that this is the residual Galois representation of rho pi. So I assume that it is absolutely reducible, and also assume that the image is sufficiently large. So this is some technical conditions which is used in the proof that I will touch a bit later. So plus some other technical conditions. Then I have these two parts of this Bloch-Kato conjecture for this standard error function. So there is the first part, the rank part, which relates the order of vanishing of this special R function at S equal to 1. Okay. This is equal to the dimension of the Bloch-Kato group. Okay. Minus the dimension of the invariant. So in fact, I can show that in this case they are both equal to 0. Second is the special R value part. Then I can show that probably normalized divided by some period, the periodic valuation of the special R value is equal to the periodic valuation of the characteristic ideal of this Bloch-Kato thermal group. So this is the result for this Bloch-Kato conjecture for this standard R function.
So 10 minutes up, so if you can wrap up, that would be great.
Yeah, so I cannot say anything about this proof. So there are mainly is to create the Peterson product to some congruous ideals, and then and also you need to prove some R equal to T theorems, that is modularity lifting theorems to relate this Bloch-Kato thermal group, the characteristic ideals to the congruous ideals, and then if you take the quotient of these two, then you will get this one, and you take the quotient of these two using the decomposition of this Young representation, you will get this one. So this is the rough idea of the proof of this Bloch-Kato conjecture. So I'll stop here.
Thank you so much.